Here I will be discussing the formation of an aldehyde via the Vilsmeier-Haack reaction. I'll first show the reaction, then discuss the theory. In this reaction, dry DMF and phosphorus oxychloride are mixed to form the reactant. You've already seen me getting the dry solvent. I've also assembled the glassware and dissolved the 7.5 grams of starting by thiophene into 40 ml of DMF. I have also put 40 ml of dry DMF in the dropping funnel. Subsequently, the solutions are cooled to 0 degrees Celsius via iced water. An ice bath is used for the lower container, and for the upper dropping funnel, an outer jacket to the glassware is filled. Once cooled, 15 ml of phosphorus oxychloride was added to the dropping funnel. Note this step can be noticeably exothermic, hence the cooling before addition. The reaction was loosely stoppered to prevent too much water getting in, but to account for any thermal expansion of gases. The upper solution was then added over 10 minutes, and the ice removed. The reaction was then heated to 60 degrees Celsius for 17 hours. Once the temperature was maintained for 30 minutes, the reaction vessel was tightly sealed. It should be noted this reaction is not done under strict anhydrous conditions. That is, a constant overpressure of inert gas was not applied. This is because while the phosphorus oxychloride is water sensitive, it is added in excess and it essentially acts as a drying agent. The deactivating effect of adding an aldehyde is used to prevent further reaction. After the reaction was completed, the reaction was poured over 300 grams of ice water. The mixture was subsequently neutralized with saturated sodium hydrogen carbonate solution. It took quite a lot of sodium hydrogen carbonate, and as such a stronger base may be preferable. The precipitate was then filtered off and washed with 4 times 50 ml of water and 1 times 50 ml of ethanol. It was observed that quite a lot of product ran through with the ethanol and precipitated in a lower flask. As such, this portion was refiltered and washed only with 3 times 50 ml of water. The reaction was subsequently dried under high vacuum, as I felt it was likely my product, and NMR confirmed good purity. However, my colleague, Anna Helaveria, convinced me that this product should be purified by column chromatography. She did this for me using a silica stationary phase and graduated the column from 0 to 10% ethylacetate in hexane. While the product does not look like it had anything separated from it according to the chromatogram, there was a large amount of seemingly inorganic impurity at the top of the column, likely an impurity from the phosphorus oxychloride. This indicated that it would likely be sufficient to run the compound through a silicon plug, washing with 10% ethyl acetate or hexane, or perhaps an even more polar solvent. Importantly, this would not have been discovered had the compound not been purified by column chromatography. The mechanism for this reaction is quite complicated. First, the phosphorus oxychloride reacts with the DMF in solution to form a Vilsmeier reagent. It is this which causes the initial exotherm. Then subsequently the Vilsmeier reagent reacts with a thiophene via electrophilic aromatic substitution. The imine bond is also reformed, removing a chlorine ion. When the reaction is worked up, by which I mean neutralized in water, the imine is hydrolyzed in water to form the aldehyde. It is the deactivation of the quasi-aromatic by thiophene system by the intermediate imine which prevents the reaction of the second portion of the Vilsmeier-Haack reagent.